last time we didn't have enough time to finish the atomic structure. We were up to first ionisation energies, the comparison. So, this is the graph explaining the trend in first ionisation energies, and that's basically the group 2 elements, and it's going through group 2, and the trend is that the atomic number rises and subsequently the first ionisation energy goes down. Sorry, one sec, that's better. The elements go down in the periods in group 2, and there's a lower electrostatic force of attraction. This is because it reflects the presence of extra shells down the group, and the reason is that because the nuclear charge increases, the atomic radius also increases. Yeah. Oh, one note that I should tell you is that when you are talking about first ionisation energies, you should always remember that if it's appropriate, you should put the quote, "It's easier to remove the outer electron." So that just gives you an extra mark, you see. Comparing first ionisation energies in a period rather than a group. So this is the graph that I am given. Sorry, it's not very good quality. Okay. So the trend is that there's a general increase. The word general is really important there. Across the period, and it results from the increase in the nuclear charge as electrons are added to the same shell across the period. As you can see, there are a few decreases, and that's seen it's when the end of a period comes and the start of a new one does. So yeah, that reflects the new shell being added basically. The atomic radius decreases, but the proton number rises. The electrons are all in the same shell. In this one there's a greater electrostatic force of attraction, more energy to pull off an electron basically. There's a blip with boron. There will be anyway, yeah, there's a blip in boron because that's at the end of a new one. There's a large decrease in the first ionisation energy when the outer electron is put into a new principal energy level. This suggests that the outer electron of sodium is in a new shell, which is further from the nucleus, and it's at a higher energy than the previous shell, since the outer electron is easily removed, and that provides evidence for the existence of principal energy levels basically. So yeah. Comparing first ionisation energies between periods, there's a question here basically which explains it all. So it says argon is at the end of period 3 and potassium is at the start of period 4. Which of these two elements has the higher first ionisation energy? So that's like practice. It's not quite an exam question, although it's like a practice question. And I've answered it quite detailedly, if that's the word, detailedly? Anyway, I've answered it with quite some detail, and I'm not going to read it all because it'd take forever, but basically argon would have the higher first ionisation energy because it's a noble gas, and so it's really hard to remove any electrons because they're all full and there's no spare ones basically. Whereas potassium is like an alkali metal, and so it's easily removed as the orbitals aren't full, the outer orbitals aren't full, sorry, and it only has one in the 4s subshell. Therefore, it's easier to remove the outer electron. There's that little quote. It's easier to remove the outer electron of potassium as there's weaker electrostatic force of attraction. So there you go. Here we are. Comparing successive ionisation energies for an element. Now, successive energies can be second, third, fourth ionisation energy. So if you don't know what that is, I'll just give you an example. So we've got second, it could be manganese. We'll go for manganese. Manganese plus, because it's already been ionised, equals manganese 2 plus E minus, and the pattern just goes on basically. So comparing those, I'll just show you my graph with my little annotations. There you are. Sorry it's back to front, by the way. It's just my camera. So the trend that you see is, again, it's a general rise, it's not just a rise. The amount of energy needed to remove the successive electrons increases as the number of electrons removed also increases. This is because a positive ion has more protons than electrons, so there's much greater electrostatic force of attraction between the nucleus and the outermost electron. It's harder to remove the next electron basically. So each time that you take one away, it gets harder and harder because it's so attached the next time. As you can see between number 3 and 4, there's a really big jump, and that's because the first 3 electrons can be removed really easily as they're in the outermost shell, whereas in the second shell it's closer to the nucleus. This shows that the 4th electron is being removed from a full shell, and so there's more electrostatic force or attraction between the nucleus and the outermost electrons. Okay? These are just summary questions, so I think that might be the end of this one. Yeah, these are exam questions now. So that is ionisation energy in atomic structure, and we've completed this booklet, guys. Woo! So thank you for listening, and next time we will be on to amount of substance. Thank you very much.